So chapter 14 is about, we're not talking about atoms anymore, we're talking about molecules. And we're going to start talking about molecular orbital theory. So that's the theory of choice when it comes to chemists and talking about chemical reactions and what's going on in the lab if you want to figure it out theoretically. So we'll start with the Born-Oppenheimer approximation, the BO approximation. Okay. Which one is, what's more massive, the nuclei or the electrons? Nuclei. By what factor?
10,000.
Well, 10,000, right? So if not more, right? Because that's just one proton. So which one should move faster, the nuclei or the electrons? Physically move faster. The electrons, right? A lot lighter. So they should. So what they're going to do, this is what the Born-Oppenheimer approximation is all about, is we're going to fix, that's what this little r is, we're going to fix the nuclei position. And this is just a diatomic molecule, right? So that distance is between this r. So they're just talking about a diatomic molecule here. But the point is let's fix the position of the A and B nuclei, those atoms, and then just calculate the energy and plot it out, change their position. Let's make it a little bit closer, plot out the energy, right? And you keep doing that for a diatomic molecule, end up with a plot like that. So if it's valid, then the Born-Oppenheimer approximation is valid. But it's an approximation, it's a guess. It may not be valid, but if it is, you get the right answers because you get a minimum in the energy. Oh, has a little E on it. E probably for well, yeah, they're equilibrium. That's the position of this that hanging. Like if you have a spring that's just hanging there, it's equilibrium position. It's minimum energy. So that would be the bond length, right, for that diatomic molecule. Some things to play around with. I think the book has bond dissociation energy. Word's kind of missing. And the symbol is DO. So DE, I don't know if you can see that. That's DE. Why is that negative? Negative energy? What type of energy are they talking about? Potential? Kinetic? When you're doing these little plots, right? You fix the nuclei of the molecule and then calculate the energy. Change the nuclei position. Calculate the energy. This sounds like kinetic or potential?
Potential.
Sounds like potential energy, doesn't it? Sounds to me like potential energy. We're talking about fixing these positions. So yeah, the electrons are moving around. Yeah, but you never really know what they're at, where they're at anyway, and we'll talk about that. But you have some probability. So it's attraction. Remember, that was the idea there. That was their convention. If you have attractive potential energy forces dominate, well, it's negative energy. Okay. But if you want to break the bond, that's DO. But DO is actually it's not quite the depth, right? Because the DE is going all the way to the bottom. But do you remember, if you really zoom up on this, we can never get to the bottom. Do you remember what this was called? You can never get to the very bottom. There's always some minimum energy. We called it the blank point energy. 0 point energy, yeah. You can never have 0. So that 0 point energy, well, I think the book just says 1/2 h bar omega. So if you want to get the bond dissociation energy, it's not just the depth of the well, right, at that equilibrium position. You have to subtract, because you can never get, right? DO would be, let's make it red. you want to break that bond, break this bond, if you want to bust it up, I guess you have to get over this height, somewhere around here. This would be DO. Well, if DE is the whole thing, right? DE is this whole mess. Then DO would be DE minus 1/2 h bar omega. Does that make sense? Wouldn't just be the depth of the well that you calculate. It's going to have to be minus 1/2 h bar minus the 0-point energy. So here's our first bonding theory. We're actually going to have two for molecules. This is just our first one, our valence bond theory. So what they're kind of thinking is that you have a bond, and it's going to be all with spin pairing of electrons. You're going to have kind of like this little idea, right? That you have to have this spin pairing to get these bonds, is what I'm kind of thinking of. But the point is you don't know whether, see, they have 1s and 2s. You don't know whether electron 1 is on atom A or whether it's on atom B. So you could take this, that's why they have the 1s and the 2s here, and they just mixed them around. But, so again, it's a diatomic molecule with atom A and atom B on each end. That's where the A's and the B's are coming from. And the two electrons that are spin paired in this bond, right, just call them 1s and 2s. You don't know if it corresponds with, if it's an atom A orbital or atom B's orbital, so that's why they have to have the sum. So there's really two of them. There's a plus combination and a minus combination. So you have two orbitals, you end up with two possible valence bond you end up with. And if you do the math, the positive combination, you see, I don't know if you can see your plus very well. The positive combination gives, oh, hey, there's some, because like this is, you're supposed to think of a nuclei here and a nuclei here. Like this might be A and that might be B. And if you want there to be a bond, well then there has to be what density? What'd you call this? What would this plot be? What are we talking about here? Why is this going up and this going down? They're trying to plot out what? Where the what is? Where the electron is. And if you want the electron to be, if you want there to be a bond, well, the electron needs to spend some time between the two. So you'd want there to be some area there. So the positive combination of these two, not the minus one, produces bonding. The minus one would be anti-bonding orbital. So you really end up with, you start with two of these orbitals, you end up with two. One is bonding, one's anti-bonding. And the bonding one is the one that has the positive sum. If you, I don't know if you remember stuff like probability density, right? Or you can call it, you might even hear the word electron density. Right, that there's non-zero electron density between the two nuclei. So if we're sticking with this valence bond theory for now, and they're talking about the hydrogen molecule, okay. Well, the first one is the different types of bonds. One is a sigma bond, and that'd be an example of this one, where there's electron density between the two nuclei. But I think you can kind of pick it out if you realize it's, I think the book uses these words, symmetric about the internuclear axis. What does that mean? Symmetric about the internuclear axis. I mean, it's not so symmetric. Atom A, atom B. Is that symmetric about the internuclear axis? Where is the internuclear axis? I was going to sketch it. Connects A to B. That's an axis, so I can keep going, right? And you can spin it. If you have to think of this as three-dimensional object, this weird lobe-looking thing. That's something that's symmetric about the internuclear axis. You see what I'm trying to get at? So if you recognize what the internuclear axis is, then you can say, oh yeah, that's symmetric. Right? You can spin it, it just stays the same, doesn't change shape. If you spin it about the internuclear axis. So it seems to work pretty good, right? They have their calculated results and they're observed and they're pretty close. What was A naught again? The Bohr radius, right? So many picometers, remember that? 55 picometers or something. So they're just divide it by A naught so they can get nice numbers, 1, 2, 3, 4. So again, they're just doing the Born-Oppenheimer approximation to get those plots. Is hydrogen a homonuclear diatomic molecule? Yeah. Homonuclear means the same. So CO would be not homonuclear, but heteronuclear. Right, that'd be CO. A pi bond, let's see how good I can. Now that you've seen this before, or you've heard of it before, sigma bond has electron density between the two nuclei. Pi bond has them where? That's so hard to draw three-dimensionally. See what I'm trying to draw? I'm trying to draw that this rectangle's a plane. It's supposed to be a plane, right? Think of this as a sheet of paper. And here's atom A and atom B, they're nuclei. So now it's not at all like this thing, right? Here's a sigma orbital because it's symmetric about the internuclear axis. This is what they classify as a pi bond. Sigma bond, pi bond.
Wait, can you explain that one?
So think of this guy. Oh, let's put in our A and B again. Well, it's homonuclear, so it has to be A and A, right? So this is supposed to be like a piece of paper, and kind of think of A and A being a plane. So you have electron density above it and below it, instead of in the middle. So I don't know, how would you draw it? So you pretty much have to take a cylinder and just empty it out in the middle. That would be take a cylinder and empty it out in the middle. And atom A is in here somewhere. The other atom A is in there. That would be a what bond? There's nothing between them. That's a pi bond. That's really what it has to be like. It can't just be up here and down here, this little plane thing. No, it has to look like that. And which type of bond, pi or sigma bond, oh man, you can't apply. Torque is a word for a twisting force. You can't do all this twisting. Which bond would prevent it? Pi bond would do. Pi bond would be very stiff. You can't twist it. You can't apply a torque to that thing. So rigid. Pi bonds are rigid. Okay. Polyatomic molecules. So now we're still sticking with this valence bond theory. And valence bond theory has this idea of promotion. And you may have heard of this. If I write carbon's noble gas core electron configuration, right, you'd look like this. Are you with me so far? Okay, so that would be the what state for a carbon atom? Ground state. This would be a excited state. So it takes energy to do this. Promotion takes energy, and this is a valence bond idea. So you take an s orbital, right, 2s. Sometimes it helps to go back to doing things this way, but we have an s orbital and 3p and 2p atomic orbitals. So how many atomic orbitals do we have total? 4. So you do this mixing thing, this mathematical, kind of like taking a bunch of clay and fudging it all together, but you end up with 4 orbitals. 4 hybrid orbitals would be what they're going to call it, right? So you start with 4 atomic orbitals, and you end up with 4 hybrid orbitals. Kind of like the conservation of orbitals idea there. But so what do they end up with? Well, you end up with sp3 hybrid orbitals. So what do they look like, right? They're all at the corners of a tetrahedron. It's a tetrahedron. That's a weird-looking tetrahedron, right? That's how I draw a tetrahedron. But everyone's got their own way of seeing stuff. Three-dimensional is hard to see, but that's how I draw a tetrahedron. But the point is at each of the 4 corners, that's what sp3 is pointed at. This might look better. Okay, so carbon undergoes sp3 hybridization. Okay, and there's 4 of them. But why could have sp2 hybrid orbital? Let's see, that's figure 1411. There's some nice pictures in there. We'll see some towards the end. I think I've got a website that shows it all. But that's on page 393. sp2, so there's 3 of them. So that's just an equilateral triangle. They're all going to point towards the corner of an equilateral triangle. Okay. I think this is kind of interesting, because I think this is important. Constructive interference and destructive interference. What are they talking about? What's supposed to be in these orbitals? Electrons, right? That's what these little arrows are supposed to be. They're supposed to be electrons. And if you want to get this shape right here, of an sp3 hybrid orbital, you want to get that shape, you need constructive and destructive interference. Otherwise, it's going to just look like this thing, this big lobe, right? This sphere. But you end up with this shape. And it's kind of there. I mean, they just didn't make it too black. They should have made it blacker. But how is this? What's this interference? Where's this coming from? This electron has to be acting like a what? A wave. To get this to work in the first place. Okay? You need the wave-like nature of matter in the first place to get this to work. So we could stop here because we're done with valence bond theory, and we're going to pretty much move on to chemists, what you see most often in journals or whatever, but is this molecular orbital theory. But right up to this point has been valence bond. But there's no homework. So that's why I'm just going to keep going. Okay, so we're switching gears, and we're going to talk about a new theory. So they all kind of run into one another, it seems like. But I think when I think of this one, I like this one because this is following through on everything that we've really been talking, at least what I feel we've been talking about with Schrodinger's equations and wave functions. And if you, like, there's probability density there, right? The point is if you have an electron, you don't know whose electrons is whose, which I kind of like because it seems to make sense. And all these wave functions are distributed over the, like look at this wave function. It's distributed over the entire molecule. So you don't know whose electrons are whose, but they're all in there somewhere. And the probability density is higher in certain locations than it is in others. It's really high between the 2 nuclei. So that would be bonding. right? So all of those ideas, I think, follow through. And they're trying to say these two things are the same thing. You ever seen this kind of map? Where the lines are closer together, that's supposed to mean what?
Elevation.
Yeah, like a huge elevation change. Yeah, when the lines are really close together. Exactly. We call these contour maps. But so both the top and the bottom diagram, they mean the same thing. So you're going to hear words like delocalized electrons. You hear delocalized electrons, they're talking about molecular orbital theory. Okay, because they're in a wave function, and the wave function is distributed over the entire molecule. Linear combination of atomic orbitals, LCAO. Another great idea that's coming out of we talked about earlier in the Schrodinger's equation. We have all these nice solutions to the hydrogen atom. They're called atomic orbitals, right? Whoa. So it serves as a great starting point to write wave functions. There's our atomic orbitals. And then you have this little c in front. It's just a coefficient. Maybe a weighting factor might sound better, right? Because the bigger that coefficient is, the more important the importance is of that atomic orbital. And it follows through like, I don't know if you remember this. You have to square the coefficient to get the probability. It's a very different way of adding probability than it is in the macroscopic world. So that's kind of what it means. That coefficient is how, the bigger it is, the more important the larger its presence is in the final wave function. So this idea of LCAO, you may have picked that one when we did Spartan. I don't remember which calculations we did over there, but there are different ways to do a lot of those calculations. But we're talking about the linear combination of atomic orbitals, molecular orbital theory. So this whole big mess. So LCAO-MO is MO found through LCAO. Does that make sense? There's going to be a number of different ways to write wave functions. And I think we're just pretty much going to be talking about this one. So that's kind of why they messed it out. So you get, here's their idea of a sigma orbital. Fits the same definition, because is it symmetric about the internuclear axis? Pretty much that dark green thing is, right? So they call that a sigma orbital. Oh, it's right here, sigma orbital. Okay. So here they're trying to mix a few things. They're trying to take the 2s atomic orbital and the 2p atomic orbital. But how many orbitals are there in the 2p? There's 3. Now they're oriented in the x, y, and z direction. Maybe you've seen the little subscripts, 2px, 2py, and 2pz. And we could sketch them out. But the point is the z is the only one that gives you, it's in the right direction to allow some nice overlap, like, and get these. So what they're mixing, they pick the 2s and the 2pz. Okay. So from each atom, you're going to have each atom, you're taking the 2s and the 2pz. So that means you're starting with 4 atomic orbitals. And then you're going to end up with 4 molecular orbitals. And all they're going to mix, like I said, is the 2s and the 2pz. They're just really talking about that second period and which atomic orbitals are we going to work with. We're going to work with the 2s and 2pz. So from each atom, diatomic, so that means you have 4 atomic orbitals total. Do the math, let it do its thing, get 4 molecular orbitals. And then they're trying to say, you see their notation here? Maybe you can tell by the colors, I'm not sure. Where's the bonding, where's the anti-bonding molecular orbitals? How can you tell? Where are the nuclei in the first place on these pictures? You should sketch them in there. Right, put in your nuclei. They didn't make them dark enough. What do the different colors represent? They're trying to, this diagram didn't bring it out. Well, it kind of did. See how plus was green and minus was blue? You change the color, you're just changing the sign. So, of that wave function. And you end up getting destructive interference here, constructive interference here. So when you ever see the two colors that they're not the same, you're going to end up with destructive interference. And it's between the two nuclei, so that's going to be anti-bonding. Down here, you've got both wave functions have the same sign, constructive interference, right? So you have bonding. Here you have, so here, and we're really interested with the electron density between the two nuclei. So that's why, I don't know if you can see it, but it's sigma. It says 4 sigma with a star. So the sigma means sigma bond. The star probably means anti-bonding. They're consistent with that. Whenever you see a star, it means anti-bonding.
Where's the star?
It's really tiny down there. It looks like this, though. 4 sigma star. Here's 3 sigma.
What did you say? You said change the color.
Change the color, change the sign.
Of what?
Of the wave function. And it's confusing. It's really confusing because when you start plotting out these shapes, you're not plotting the wave function anymore. You're plotting out the probability density, right? Psi star psi, d tau, in all 3 dimensions. At r squared dr, sine theta d theta, d phi. So it's a big, ugly mess. But luckily, we don't have to do all that. We're just looking at the end results. And notice here we're interested in the electron density above and below. So now we're talking about pi. So if you blow that up, you can see that says 2 pi star. This one says 1 pi. So again, you have anti-bonding, pi bond, or anti-bonding molecular orbital, and bonding molecular orbital, 1 pi. Oh, okay, I remember now. If you're going to list these out in energy, 2s is probably here. This 2pz is a little bit higher in energy, right? And if you're going to, if this is going to be bonding 3 sigma, it needs to be below. It needs to be below the energy of 2s. If you're just going to. That's why it's bonding. Because when you mix these orbitals, if it's lower in energy than what you started out with, yeah, that's bonding. Right? Higher, like where's my sigma? What's that, 4 sigma star? 4 sigma star would be higher in energy than the 2s. Okay. That's another reason why it's anti-bonding. It'd be better to stay in the 2s. Okay. Some more terminology. The overlap density, right? Showing that, okay, see we have electron density here between the two nuclei. The electron density there. They call it overlap density because, yeah, we're actually trying to overlap the wave functions and see if there's constructive or destructive interference. And if there's electron density between the two nuclei or above and below them, like a pi bond, you get a bonding orbital, right? So this figure 1416 would be a bonding or anti-bonding orbital. It would be a bonding. This one would be what? A anti-bonding. And they're trying to say why here. They're trying to say that, okay, remember the black dots are the what? Are the nuclei. So if you have case 1, this would be case 1. Case 2, this would be case 2. And they're trying to say, okay, these are the nuclei. Nuclei are what charge? Positive. Electrons are negative. So they're just attracted to the center because that's where the electrons are. Right? That's negative. This is positive. If the electrons are hanging outside, okay, well, positive, negative. There's nothing really changes. I mean, the attractive forces are still there. Now they're just, that's where they're attracted to. Regions that aren't between the two nuclei. So they're attracted elsewhere. Sigma electron, just an electron in a sigma orbital. We're not drawing electrons in sigma orbital. What we're going to be doing is we're going to be drawing little energy diagrams like this. Molecular orbital energy diagrams. And that'll make a lot more sense. When you put an electron in a molecular orbital, that's a sigma, they call it a sigma orbital. We're not there yet, though. But that's kind of where we're headed. Anti-bonding orbital. Talked about that already, kind of. They're trying to get across the words of a nodal plane here, but that's kind of hard to see. That there's a plane here that's actually a node. It's hard to see, but and then to what some of these molecular orbitals look like. Let's see if this works. Okay, so here's our 2s orbital. Right. So you've probably seen these kinds of pictures before, right? Of our atomic orbitals, our x, y, and yeah, 2pz, 2px, and 2py. The atomic orbitals we've kind of seen, they get some funky shapes, right? The more nodes, the higher the energy. Okay. Man, someone could make artwork out of this stuff, don't you think? Okay, so molecular orbitals. Sigma star. And here they're kind of trying to animate what it looks like to make one. And it's star, so it's anti-bonding. So here's a nuclei, there's a nuclei. You're not going to get any overlap density, non-zero overlap density. But the bonding, nitrogen, it must be anti-bonding. Here's another anti-bonding. So to do these calculations would be, oh, that'd be so horrible. Here's finally a bonding. So molecular orbitals, you don't know whose electrons are whose. They're just wave functions that cover the entire molecule. Okay. So look at that. You only have 2 homework questions. I mean, how easy could this be? Guys, man, you got the right class, didn't you, Gloria? A exercises, number 8. Change the denominator from the cube root of 3 to the square root of 3. Hint, page 388. Okay, let's see what the heck they're talking about. Okay. Show that the sp2 hybrid orbital, s plus, what's to the 1/2 power mean? Square root. So s plus the square root of 2 times p divided by 3 to the cube root, but cube root is supposed to be changed to the square root of 3. Show that it's normalized to 1 if s and p orbitals are normalized to 1. So this isn't a bad question if you just realize what they're trying to get you to do. They're trying to show you that, they're trying to say that, okay, first we can start with our, if we say something's normalized to 1, what expression do we write? Psi star psi equals 1. It has to be the integral of it too, right? And our d tau and all that fancy stuff in there. And it says show that. It's on the right question mark over it. Okay. And they're giving it to you. They're giving it to you. This is what our psi is. All right. Now they say it's of the sp2 hybrid orbital, so if you want to write a little sp2 on there, if you make it look better. All right. Maybe subscripts kind of help, but maybe they don't. And the s and the p, we're not even looking at all the ugliness of it. They're letting us really cheat because they're saying s is this is the function, this big ugly function of the s orbital, right? P. So that it goes to show that if the s and the p orbitals are normalized to 1, so what expression would you write with just this one comment? Because we have to show this. We're going to show that, but we want to get the rules of the game down here first. If s and p orbitals are normalized to 1, that would mean what? 1 has to equal the integral of, because 1 has to equal psi star psi d tau. So you could, whoops, psi star psi. You could write this, but it's not really, they want s and p orbitals. So what I'm saying is instead of writing psi's, let's write s. See how they're really letting you by here. And if you say, oh, p orbitals, well, then you write 1 equals the integral p star p. And we don't even really care, thank goodness, the ugly mathematical function that these things are. We're just trying to say, let p be this ugly thing, right? Let s be this ugly thing. But they're saying that they're normalized. Okay? So you see what's going to happen here now? You're going to substitute in this expression, except they want that to be 1/2, right? That was our hint. Do you see that? So you substitute this expression in right down here, and you substitute it in there. Except when you put it in where there's a star, make sure you put a star on what? The s and the p. Exactly. So substitute in that sp2 hybrid orbital wave function, complex conjugate, and then you just copy it in again, but no complex conjugate, d tau, multiply them through, and this stuff is going to help you simplify it. See if you can get it to work. You can get all your homework done.
But it wouldn't be detail anymore, would it?
Yeah, because we have detail right here. I think the part that's gonna, if you multiply these out, you're not just gonna get S star S, P star P. Aren't you also going to get like S star times P or P star times S? Aren't you gonna get some of these guys too?
Mm-hmm.
You see that, Gloriana? You're gonna get some of those. There's a word for this. You say it equals 0. Orthogonal. Geez, I should toss you a brownie. Orthogonal. Orthogonality. So those terms that are different, you just set them to 0. That's one of the big reasons why they pick this linear combination of atomic orbitals, because they're orthogonal. It makes calculations so much easier. So hopefully you'll end up with 1 equals 1. So S star P detail is orthogonal. P star S orthogonal. They have to be the same.
Okay, so after we plug this in, like, we just, I don't know, we just distribute it?
Yeah, exactly, just distribute it. So you have to have stars by these guys. A star, this is psi star. So you have to have S star and P star.
Is there going to be S star S?
All right, so then, yeah, you can have an S star S, you can have an S star P, and then you're going to have an S, sorry, then this one, P star S and a P star P. So P star P's, they're all known. Well, oh yeah, you got to do that too. You got to keep in. I'm just doing the hard part. That's why we had to change that cube root of 3 to the square root. They messed up. And remember, those numbers you can pull out of the integral.
But the square root of 2, is it attached to the P star?
Well, it's a number, so you can pull it out of the integral. So you'd have this, when you take this one through, S star times square root of 2P, like even the square root of 3 thing you can pull out of the integral, right? You pull that square root of 2 out. All you're left with is S star P. So I'd pull that 1/3 out of there. Definitely pull that out of there. Right? Get all the S star S's and P star P's, set them all equal to 1, those integrals. Don't forget about your square root of 2 parts. something like that. There's 1. That guy's 0.
But the square root of 2 you didn't pull out?
Yeah, but it's times 0 anyway, so you don't care. It looks easy if you pull out the square root of 2, because then it's easier to see S star P.
I hate normalizing wave functions. They piss me off.
Yeah, they're meant to make your life easier.
I hate it. I hate it so much.
Well, then you better get started on the next one, because it's the same kind of question, number 9. Just get through it. Get used to it.
Time to go.
Is it really?
Yes, it is. 35.
Okay. Well, do both. These are both very similar. Okay. So what do you see how to set this one up? All you're going to do is to show that the bonding and anti-bonding combinations are mutually orthogonal. So orthogonal means set equal to 0. So the plus combination and the minus combination. See if you get 0. And it's everything you said, everything that works just like before. They say that in the sense that their mutual overlap is 0. So in other words, integral of psi A, psi B will be 0. The ones that were the same, AA, would be 1. Right? And that's the game you got to play. Just like you did with number 8.